Great. So last time I made a critical mistake when I defined time inhomogeneous. I should have defined it as time homogeneous. So let me just correct that quickly. So a Markov chain is time homogeneous if, well, I wrote it as probability that xi plus 1 equals, or maybe I said xi equals zi, given xi minus 1 equals zi minus 1 is independent of I. So this is kind of a pretty bad mistake. I had said inhomogeneous, but it's supposed to be homogeneous, which makes more sense, right? Because it's like it doesn't, like it's the same throughout time. One second. Okay, but now I can continue with where we were last time. So let me recall, I think I had this definition. So we have a Markov chain which I'll represent by P. So P is the transition matrix of the Markov chain. And we have an element X in our state space script X. We're going to let the period of X be the GCD of the set of I such that P to the I of XX is positive. So it's the GCD of all of the times at which you can return to X. Okay, and then we had this proposition at the end saying that if X communicates with Y, meaning that there's a positive probability of getting from X to Y in some number of steps, and there's a positive probability of going from Y to X in some number of steps, then they have the same period. Okay? So then, that means that if we have an irreducible Markov chain, meaning that there's only one class, then we can define its period to just be the period of anything in the class. So if P is irreducible, its period is pair of X for any state X. And we'll say that it's aperiodic if the period is 1. So P, yeah, I'll just, so say P is aperiodic if its period is 1. Okay, so here's another proposition. Suppose the period is K. Okay, so suppose P has period K. Then there exists a partition of X, so I'll just say a partition of X into some disjoint subsets, so into sets C1 through CK, such that the probability of going from x to y is positive if and only if x is in one of the sets Ci, and is this right? If and only if x is in Ci and y is in Ci plus 1. I think this is not correct. Because I think it shouldn't be an if and only if, right? Because like even if the period is 1, just saying that x and y are in the same class doesn't mean that there's a positive probability of going from x directly to y. So I think what it should be is just one direction, where if the probability is positive, then like they're in consecutive subsets. So this should be only if. I think. Okay. I won't prove this, but basically the way that you can think about this is you have like some transition diagram and you can break it up into these k blobs so that all of the arrows go from like, basically they form like a cycle of size k, and all of the arrows go from one blob to the next blob in the cycle. So the picture looks something like, maybe all of you have a bunch of states like this, and all of the arrows in the transition diagram go along in a cycle like this. So these are your sets C1, C2, C3, C4. Your K is 4. Yeah.
Just a notation question. When you write like the P, like I, X, X, or like P, X, Y, do you want us to write the P as a capital P or lowercase p?
Oh, I think capital P. Yeah, these are supposed to be capital. Yeah. Maybe I'll. So this is my capital P. This is my lowercase p. Okay, so now let me define actually a stationary distribution. So I mentioned stationary distributions last time, but I'll give an actual definition. So a distribution pi on the state space X is stationary for a Markov chain P if, well, I'm going to write it as pi P equals pi. So remember, we can think of pi, so it's a distribution, we're going to think of it as a row vector indexed by the states. And so like the entries of the row vector are just the probabilities of the various states in this distribution. And then P is a matrix, so this is just multiplying a row vector by a square matrix. Right, so that's a stationary distribution. Another way of saying this, so equivalently, this means that if x0 is distributed according to pi, so meaning that like we choose our first state by sampling according to the distribution pi, then x1 will also be distributed according to pi. Okay? So this is going to be relevant, as I was saying last time, to when we look at like the long, oh yeah.
So sorry, when you define a Markov chain as having like period k, what does that mean? Because we talk about period in the context of like a point, right?
Yeah, so I think I'm just saying this. Oh wait, did I? Oh, wait. Did I not? Maybe I just said this. sorry, yeah, okay, so I should say, I see, I didn't define that. Oh, right, what am I saying? Is that written here? Hold on. So probably this should mean, yeah, I guess that isn't written in these notes. Probably it should just mean the GCD of all of the periods, of all the states. I think that's what I want to say. Yeah. Yeah, I think that's probably
Okay.
right. Yeah.
Yeah.
Yeah. So yeah, thank you. Maybe I'll put that here. Period of P is period, or it's the GCD of the set of, well, periods of X such that X is in X. Okay. Right, so we'll find that, well, okay, I guess the point is that if you have like the limiting distribution of some Markov chain, so like if we assume that the limit as t goes to infinity of the probability that x t equals y given x0 equals some x is some pi of y. So like we're assuming we have some distribution pi such that for any x and y, or maybe for any fixed x and for any y this holds, then pi is just, it has to be a stationary distribution, just by like, you know, taking, well, yeah, I think it's a simple argument. But anyway, it has to be a stationary distribution. Okay, then pi must be stationary. So, while in general stationary distributions aren't going to have to exist, I mean, one simple example of this is like, imagine you have a Markov chain that isn't even random, it's just deterministic. Maybe your state space is all of the integers, and at every step you just move you know, to the right by 1 on the number line. Well then, there's no, you're not going to have a stationary distribution just because like here, there's no, this limit isn't going to exist. So, or I mean, sorry, the limit is going to be 0 everywhere, I should say. If you start anywhere, then the limit of the probability that you're at state y for any y, that's going to be 0, and then that's not going to be a probability distribution. So, in general, you're not going to have stationary distributions, but a lot of what we're going to look at is finite state Markov chains, and they are going to have stationary distributions. So, theorem, let P be a Markov chain on a finite state space let's say X. Okay, then P has a stationary distribution. Okay. This, if you're familiar with like the Perron-Frobenius, oh yes.
Sorry, I think I missed this, but what does it mean for the x0 to be equivalent to the distribution?
Yeah, sorry, what I mean by this is you have a distribution, and you can think of this as like, this is distributed according to that distribution. So like one way you could think about a Markov chain with the initial state is that maybe you choose one particular state and you say, I'm going to start here. Or you could say, I'm going to randomly choose the initial state. And the distribution that you use to choose it randomly, is some distribution like this. So here I'm saying that pi is some distribution that assigns a probability to each one of your states, and I am choosing my starting state randomly according to that probability distribution. And I'm saying that if you choose the first state according to that distribution, and then you do one step of the Markov chain, then now you have a potentially different distribution on what the next state could be, because it's influenced by this transition in the one step of the Markov chain. But this is saying that if your initial distribution was stationary, then actually the new distribution you get is the same distribution. Yeah. Okay, so this is a consequence of the Perron-Frobenius theorem, but I think I'm going to prove it separately because this proof will use what are called stopping times, and that'll be something that we'll talk about later, so I think it's worth going through the proof that's specific to Markov chains here. And we're going to this also has the advantage of constructing the stationary distribution in a concrete way, so that's kind of nice. Okay. Oh, maybe, yeah, another remark I should say is that, well, what is a stationary distribution? If you think about it linear algebraically, it's just an eigenvector of eigenvalue 1. Think about it in terms of just multiplying matrix with row vector. And that will exist, but it's not clear why. So it exists because this matrix has all of its rows summing to 1. Okay, so it's going to have an eigenvector of eigenvalue 1, but it's not clear a priori why the entries should be non-negative, right? So you want actually this to be like a probability distribution, so you don't want to have negative numbers. Okay, so to prove this, let me make a definition. So I'm going to let, well, let's say, suppose I have a state x. We're going to let tau x plus be the minimum index I that's positive, such that xi is x. Okay, so this is like the first time that you, given that x0 equals x. So if you assume that you start at the state x, this is the first time that you return back to where you started. And if you never return, so if you never return, then we'll just say it's infinity. So this is infinity if this set of I greater than 0 such that xi equals x is empty. Okay, so this is some random variable where it takes values in the positive integers, and we're going to look at its expected value. So let's see, this is kind of a weird, whatever. Okay. Yeah, so here's a proposition. If P is irreducible, and x is finite, then the expected value, then for any x, for every x in x, the expected value of this random variable tau x plus is finite. Okay. So this is just saying that if you have an irreducible Markov chain, the expected amount of time needed to return to where you start is not going to be infinity. So why is this? Well, okay, proof. So since P is irreducible, there exists some epsilon and some r, let's say some positive integer r, such that okay, this is the quantifiers are a little weird here, such that for any x and y, I want to say in x, there is a j less than r, such that p to the j of xy is greater than epsilon. Okay, so what is this saying? It's kind of confusing. So we can find some epsilon and some large r, such that if you take any two states, then there is some time before that large r, such that there is a reasonably good probability of going from x to y in that number of steps. Yeah, so maybe the informal way of saying this is that for any x and y, there is some somewhat small time, somewhat small time, such that within that amount of time, or okay, there's some time such that within that amount of time there is a reasonably good chance of going from x to y. Okay, maybe that's a way of saying it. Okay, so what does this mean? Well, let me move to a different board. Okay, then what this implies is that for any value of xi, so no matter what the state xi is, the probability of hitting the state x between times I and I plus r is at least epsilon. Okay? So if you're at some state, then within this amount of time, within time r, there's at least an epsilon chance that you'll hit the state x. Okay, so what this means is that, well, then, okay, so this just implies that the probability that tau x plus is greater than, so for some integer k, it's the probability that it's greater than kr is less than 1 minus epsilon to the k. Because in order for the first return time to be bigger than kr, that means like during the first r steps, you don't hit x, and the probability of that is less than 1 minus epsilon. But then the probability of not hitting x again in the next r steps is less than 1 minus epsilon, and those are independent. So the probability is less than 1 minus epsilon squared, and then you just keep going. In the next r steps, you get another 1 minus epsilon. So in total, you get 1 minus epsilon to the k as an upper bound for this probability. And then I also just want to mention, so recall, this is sort of just a standard fact about expected value. Recall that the expected value of this random variable tau x plus can be written as the sum over integers I at least 0 of the probability that tau x plus is greater than I. So this, if you haven't seen this, this could be an exercise. It's just you write out the definition of expected value and you rearrange the sum, and this ends up being true. Okay. Well, okay, so what does that mean? Well, then that means that the expected value of tau x plus is less than or equal to the sum. So if we use this, it's less than or equal to the sum over k at least 0 of r times the probability that tau x plus is greater than kr. Right, so I think that just is coming from this sum, but saying like let's group it into clumps of size r. All right, so like if you look at the first r integers I there, then that would give you an upper bound of the probability that it's bigger than, yeah, okay, maybe I should spell this out actually. I think it's not hard, but the point is, so I could say this is the sum, it's equal to the sum over k at least 0 of the sum, okay, I'm going to say I goes from k r to k plus 1 r minus 1. So I'm clumping it into this chunk of size r for each k. And then I just take that, so probability that tau x plus is greater than I. But then the point is that like, if I is in this range, then the probability that tau x plus is greater than I is going to be less than the probability that it's greater than kr, right? Because being bigger than I, right? I is at least kr in this range. So if you are bigger than if you're bigger than I, then you're also bigger than kr. So this is certainly less than or equal to just, well, I'll say this way, sum from I equals kr to k plus 1 r minus 1 of the probability that tau x plus is bigger than kr, but this doesn't depend on I, so actually there are just r terms here, and, or no, yeah, there are r terms here, so I can just bump this into sum over k at least 0 of r times this thing. And then by what we just said, this is less than or equal to r times the sum over k at least 0 of 1 minus epsilon to the k, and then that's finite just because it's a geometric sum. Okay, so we know this is now finite, and then now we can prove that there's a stationary distribution. Okay, so proof of the theorem. Are there any questions up to here? Yes.
So that first thing that you said, where like since p is irreducible, there exists an epsilon greater than, like that part, is that obvious or like is?
Yeah. So right. Since it's
Like
irreducible.
the bottom line of that board.
Oh.
Is that like?
Oh, I see. Okay, there exists epsilon. So right, I think the point is that you have finitely many states. So like for any x, you know that there's a positive probability of going to some other, of going back to itself actually, right? Like it's irreducible, so for any state, there's a positive probability of going from x to this other state. And then in particular, there's like a positive probability of returning to itself. If you think about it in terms of like a transition diagram, you just sort of look at like what is the shortest path from x to itself, and that's going to give you some positive, there's going to be some positive probability of going from x back to itself along that shortest path. And then you just say, well, let me maximize the length of this shortest path over all states x, and that should be your r, saying that like, you know, for any, wait, is this true? Oh, maybe I need it for any x and y. Yeah, maybe I want to say, okay, for any x and y, there's a shortest path from x to y in this diagram, and you get some epsilon depending on x and y, and some length of the shortest path. But then you just say, if I do this for all x and y, I'll take the maximum of these shortest path lengths, that'll be my r, and I'll take the minimum of all of these epsilons, that'll be my epsilon, and then it should work. Yeah. Okay.
Sorry, can you re-explain that? What do you mean by the national?
Yeah. Okay. Maybe I should make a picture of this. Yeah. So let's say I have like, I don't know, 5 states like this. So maybe I have like a, you know, 0.1 chance of going here, and then maybe here I have like a 0.2 chance, and here maybe this is like a half, and maybe here's like, I don't know, a fourth. I don't know if I want to draw the whole thing, but the point is, okay, I have a bunch of arrows. Maybe this is 0.9, and it should be irreducible. Okay, something like this. And if I pick any 2 states x and y, you know, maybe here's my x and here's my y, and I say, well, okay, I know that if I start at x, the probability of going from x to y in 2 steps is, well, okay, I haven't filled out the diagram, but let's say it's like 0.1 times 0.2. Okay, so there's at least a 0.1 times 0.2 chance of going there in that many steps. So this is some small epsilon depending on x and y. And the number of steps that it took was 2. And I can do this for any 2 x and y because it's irreducible. So for any x and y, I'll get some epsilon depending on x and y, and I'll get some length of like how many steps it takes. And then for this fact here, I'm just saying, well, take your epsilon to be like the minimum of all of those epsilons that you needed for choices of x and y, and take this r to be the maximum of all of the lengths that you needed. Because, right, r is sort of like an upper bound on how many steps you're going to need to get from x to y in this statement. Does that make sense? Okay. So maybe I'll come over here. So let's now prove the theorem. Okay, so let's fix. So we have now just an arbitrary Markov chain with a finite state space. We're not assuming it's irreducible, but we know that there's at least one closed class. I think I said this last time. So fix Z, so this is some state, in some closed class. Okay. So what I want to do is consider the Markov chain started from Z. So consider the Markov chain with x0 equals Z. And now for any x, I want to let n sub x be the number of times we visit the state x, the number of visits to x, before we return to Z. Or in other words, before time tau z plus. Okay, so tau z plus again is the time that we first return to the starting state z. And if I have some other state x, I'm just saying this is the number of times that we visit x before returning to z. This is some random thing though. This this is a random variable. Okay. And then what we're going to define is we're going to define pi of x. So for any state x, we'll define pi of x to be the expected value of in sub x divided by the expected value of tau z plus. Okay. And the claim is that this is going to be our stationary distribution for the Markov chain. Okay, so here I had a proposition about when P is irreducible, but because we started at Z and Z is in some closed class, we're never going to leave that closed class. So we can kind of just restrict our attention to that one class and pretend that it's an irreducible Markov chain, because just we can forget about everything that's outside of that class because we're never going to see it. So just, I guess, view the Markov chain as an irreducible Markov chain on the closed class containing Z. Okay, so we know, first of all, okay, so this tells us that this is actually finite, so like we're not dividing by infinity or anything here. But also note that the sum over all x of n sub x is tau z plus, right? Because this is just like the sum, like, right, you're just summing over for each state the number of times that you visit that state before reaching tau z plus, and if you just sum that up, then you're just going to get tau z plus. Okay. So that means that, like, if you take expected values here, then that's telling you that the sum of these should be 1, so it's actually going to be a probability distribution. So pi is actually a probability distribution. Okay, so now we want to show that it's stationary, meaning that pi p equals pi. Okay, so what we're going to do is, well, we're going to do a computation. Okay, so let me do this computation here. Okay, well, first of all, I guess what this is saying is, yeah, maybe I should write out, okay, what does this actually mean? I want to take the sum over x of p of xy pi of x equals pi of y. So then this should be true for any x, or yeah, for any x and y. This is what you get by just doing this multiplication of this row vector with this this matrix, and saying you want this the entries in these two vectors to be equal. well, that ends up just saying this. Okay, this is like the y entry on the right-hand side, and this is the y entry on the left-hand side. Okay, but then I can rewrite this as, okay, well, it's the sum over x of p of x, y, expected value of in x over expected value of tau z plus, and I want this to equal the expected value of in y over expected value of tau z plus. Let's just cancel this because we can, and so now we want to prove this. Okay. So this is what we want to show. Maybe I'll put like a question mark to say like, okay, is this true? Or okay, maybe I'll say like, we want this. Okay, so now we're just going to compute some things. So let's look at the left-hand side. Sum over x of p of xy, expected value of in x is, okay, well, we're going to write this as the sum over x of the sum over I at least 0 of the probability that xi equals x and tau z plus is greater than I. Okay, or maybe I'll write greater than or equal to I plus 1. Right, because this is just, basically I'm summing up a bunch of indicator vectors. I'm saying that, like, for each I can look at the event that xi equals x, and we haven't returned to z yet at time I, which is the same as saying that tau z plus is at least I plus 1. And in sub x is just going to be the number of times that this happens, right? Because it's, by definition, it's the number of times that you returned to x before you've come back to z. So it should just be this, the expected value should just be the sum of the expected values of these indicator events. So it's just the sum of these probabilities. Does this make sense?
Sorry, could you just explain how you got from the bottom line of the top block? So we want to show that pi p equals pi to the statement below that.
Sorry, from here to here?
No, from the one above.
From here to here?
Yeah.
Right, yeah, okay, maybe I should do this. So it should be just like multiplying a row vector, right? Like if I think of this, maybe I have, okay, let's say I have like 3 states, 1, 2, and 3. So I have pi of 1, pi of 2, pi of 3, and that's my row vector here. And then p would be like p of 1, 1, p of 1, 2, p of 1, 3, and so on, p of 2, 1, p of 2, 2, p of 2, 3, p of 3, 1, p of 3, 2, p of 3, 3. And I want to multiply these. Okay, so what I do is, like, let's say I want to look at the, so okay, I'm going to multiply these. And what's the first thing that I should get? Well, it should be pi of 1, p of 1, 1. Right, so I have like p of 1, 1, pi of 1, plus pi of 2 times p of 2, 1, pi of 2, plus p of 3, 1, pi of 3. And this is like, this is the first entry in my row vector when I multiply this. So it would be like this, but then there's like a second term and a third term that I won't write. And so what is like the, okay, so this is the first entry, and I want that to equal the first entry in pi, which is just pi of 1. So in order for the first entry here to be equal to the first entry here, I want this sum, which is just this thing, right? It's the sum over, let me make sure I got it right. It's the sum, here y is 1, so it's the sum over x of p of x1 pi of x. Right, so this sum here, when y is 1, it's this thing. When y is 2, it would be the second thing. When y is 3 is the third thing. And I want that to equal the corresponding entry in pi. Does that make sense? Okay, cool. Okay, so over here, we have this. And what are we gonna do next? Oh wait, sorry, I missed something. Wait, yeah, maybe oh, I forgot y. Yeah, there's no y in here. Okay, so it should be this, sorry. There should also be a probability that xi plus 1 equals y, given that xi equals x, and tau z plus is at least I plus 1. Okay, right, because yeah, why is this? Yeah, so if xi is x and tau z plus is at least I plus 1, then the probability that xi plus 1 equals y, that's just this, right? Because p of xy is just the probability of going from x to y. Maybe a better way of saying that, sorry, you have a...
Wait, I was just gonna ask, like, wouldn't that be greater than pxy since you know you're not going to... Oh wait, oh, never mind.
Yeah, so I think what I want to say is... Yeah, I mean, I think this works. Yeah. Okay. But now I can do this. I can rearrange the order here and write this as the sum over I at least 0 of, well, if I sum this over x, then I'm saying it's the probability that xi equals x and tau z plus is at least I plus 1 times the probability that xi plus 1 is y, given that that is true. But if I sum over x, then this should just be the same as the probability that xi plus 1 is y and tau z plus is at least I plus 1. So maybe I'll write that out. Xi plus 1 equals y and tau z plus is at least I plus 1. Basically just because xi has to be something. So if I sum over all of the possible states, then it has to, yeah. Okay, let me shift the index and just say this is the sum over I at least 1 of the probability that xi equals y and tau z plus is at least I. Okay, so I just shifted the index. Is there confusion? Okay.
Wait, sorry, can you just go over how you got the first equality on that board?
Yeah, so this one.
Yeah.
Yeah, so what I want to say is maybe it's helpful to write this as the probability that xi equals x and tau z plus Okay, yeah, so maybe what I wanna say is this. This should be the sum. Oh, okay, I can't write there. Let's write it as the sum over x of the probability. Okay, so this is sum over x of the sum over I at least 0 of p of x y, and then the probability that xi equals x, and okay, I can't draw an ampersand, and tau z plus is at least I plus 1. I think maybe that works.
So that's just like a tail sum expectation.
Yeah,
Okay.
right. Yeah, and I think it's just like, yeah, so I have just this probability just comes through. But then, like if xi, so what I can say is if xi equals x, then p of xy is the probability that xi plus 1 equals y. So I could write this as the so it's sum over x, sum over I, of the probability that three things happen. One is that xi equals x, and the next is that tau z plus is at least I plus 1, and the third is that xi plus 1 equals y. Okay? But then, the definition of conditional expectation is that, like, the probability of A given B is the probability of A and B divided by the probability of B. So I could write, like, what this is just, it's the probability that xi plus 1 equals y, and xi equals x, and tau z plus is at least I, divided by the probability of this, which is this thing. Right, so if you just unpack the definition of conditional expectation, then this product is exactly just this, the probability of all of those.
Okay. So pxy is probability of getting to x from x to y in exactly one step.
Yeah.
So how would we represent like the probability of getting from x to y, like when we're talking about if two things can communicate?
Wait, sorry.
Like how would we represent the probability of like getting from state x to state y in like some finite number of steps? Like how did we?
I mean, I think there I was just saying like, well, okay, the probability of getting from x to y in some finite number of steps.
I thought we also used p x comma y for that as well.
Well, I think I was saying like p to the I of xy would be the probability of getting from x to y in I steps.
Mm-hmm.
So, like, is that what you're
So I guess
saying?
you can just say like the sum of all p to the i's.
Yeah.
Okay.
Yeah.
All right, that makes sense.
Okay. Does this help? Okay. Yeah, maybe I should have written that out. Okay, so here, now we have this. And, okay, what do I want to do with this? Well, I want to write this as, I want to break it up into, yeah, let's write it as the sum over I at least 1 of the probability that xi equals y and tau z plus equals I, so not greater than or equal to, but equals, and then plus the sum where it's bigger than I. And then how can I write this? Well, this should be, well, okay, let me do this. Let me add in the 0 term. So I'm going to sum over 0. But then I'm going to subtract it away. So I'll subtract the probability that x0 equals y and tau z plus is at least 1. Okay. Well, if, wait, oh, okay. If x0 is y, then I want to say that tau z, oh, okay, tau z plus is always at least 1, right? It's defined to always be 1. So I don't actually need that condition here. Okay, so we're going to write it like that. And then finally, what is this? Well, that is just the expected value of n sub y by the same thing that I did up there. Right, like up here I said the expected value of n sub x is the sum over I at least 0 of this thing, and now you can see I have exactly like, why is there a 0? Okay, hold on. X. Okay, so what is this? This is the probability that x sub tau z plus equals y, right? Here I'm saying xi equals y, and I is tau z plus. Okay, so that's just the same as saying that x of tau z plus is y. And then this thing is exactly this with x replaced by y, and I was saying earlier that that is just the expected value of n sub x. So this term here is the expected value of n sub y. And then I subtract away the probability that x0 equals y. Okay, and then there's one last step, which is just, well, I want this to be equal to expected value of n sub y, right? Because I'm trying to get this, so I want that. So the point is that this should cancel with this, and the point is that if so I assume that x0 is z, right? X0 is z. So if y is z, then this is 1, because x0 is z, so the probability that x0 is y is 1 if y is z. But then also, this is 1, because like by definition, what is tau z plus? It's the time that you first return to z. So x of tau z plus has to be z. So this is saying like it's the probability that z equals y. And this is also the probability, because this is also z. Yeah, maybe the point of this is just like, by definition, this thing is z, and this thing is z, so those cancel. Yeah. Okay. Is that good? Yeah.
For the last 2 lines on the top board, so the first 2 expressions are, oh, there's an equal to sign. Oh, I see. I see you split it up. So you took one term out and then the rest on the other side.
Yeah, so here?
Yeah.
Yeah, right.
Got it, thanks.
Okay, so the next thing we want to do, so we know now that there's a stationary distribution, and what we want to say is that if we have an irreducible Markov chain, and a lot of the Markov chains that we're going to care about are irreducible, then we want to say that actually there's a unique stationary distribution. Again, if there's a finite state space. And so then we'll be able to talk about like the stationary distribution nice. Okay. So if x, oh, maybe I'll write it as a theorem. If the state space X is finite and P is irreducible, then there's a unique stationary distribution. Okay, so proof. Well, let's start with two stationary distributions. So let pi1 and pi2 be stationary distributions. And we want to show that they're the same. One thing you can check, this is kind of just a technical point, but it ends up being true. Maybe I'll put this on a p set or something. I'll just say, okay, fact, pi1 of x and pi2 of x are positive for all x. Okay, so maybe I'll just, that'll be a p set or something. Okay, so that's positive, which means that we can divide by them. That's the only point. I just want to make sure I'm not dividing by 0. So let's find some z, some state z in X that minimizes this ratio pi1 of z divided by pi2 of z. Okay. So then, okay, pi1 of z divided by pi2 of z can be written as the sum over x of pi1 of x over pi2 of x times pi2 of x times p of xz divided by, okay, well, we can unpack this, the sum over x of pi2 of x, p of x, z. Why is this? Well, okay, so what is this? This is the sum over x of pi1 of x, p of xz. But because pi1 is stationary, that would be the same as pi1 of z. Okay, so this is like the same computation that we did over there. This is pi1 of z, and then similarly, because pi2 is stationary, this denominator is pi2 of z. Okay. And okay, it says, and this would lead to a contradiction if pi1 of x over pi2 of x was bigger than pi1 of z over pi2 of z for any x. Okay, why is this? so if pi 1 of x over pi 2 of x is bigger than pi 1 of z over pi 2 of z, yeah, for any x, yeah, for some x, this can't, yeah, this is impossible. Okay, so why is that? Well, the point is that this is like a convex combination of this pi 1 of x over pi 2 of x. Like for each x, you have this quantity, and you're sort of averaging it, divided by the sum of these. And if one of these values was bigger than pi 1 of z over pi 2 of z, then this whole thing would be bigger than pi 1 of z over pi 2 of z. Yeah, I think the way you should think about this is like, this is a weighted sum, where you're summing like this quantity over x, and each one is weighted by this weighting factor. So this is some kind of averaging. But when you do this averaging, if one of the things that you're using in the sum was bigger than this, then the average would be bigger, because we know that all of these are greater than or equal to this, because we chose this minimally. Okay? So the point is, none of these pi 1 of x over pi 2 of x can actually be bigger than pi 1 of z over pi 2 of z. So they all have to be the same. So pi 1 of x over pi 2 of x equals pi 1 of z over pi 2 of z for all x, so that they all have the same ratio. And then, okay, yeah, so the ratio is constant, which means that actually pi 1 and pi 2 have to be the same because they're probability distributions. Okay. And let me just mention maybe a corollary of what we're doing here. Corollary. If P is irreducible and X is finite, then the unique stationary distribution is given by pi of x equals 1 over the expected value of this tau z plus, where z is just some, oh wait, sorry, pi of z, I should say. So this is like a nice formula for the stationary distribution. It's just 1 over the expected amount of time needed to return to the starting point. And okay, why is this? Well, we just saw, so proof, we saw that expected value of n sub x over expected value of tau z plus defines like this quantity. If I define pi of x equals this for all x, then this defines a stationary distribution. And so it must be the stationary distribution. But now just take x to be z. So set x equals z, and note that, well, what is n sub z? N sub z is the expected number of times, or yeah, it's the number of times that you return, or that you hit z, like before returning to z, but you started there, so like there's one time, which is like the starting time. So this is just 1. Okay, so I think next time we'll actually start playing with particular Markov chains. I think we had to start with like just the general definitions and sort of theory of stationary distributions and stuff. But I think things will get more fun when we actually like work with particular Markov chains. Okay, I think that's all for today.
Why was it impossible for